Hello and welcome to ACSC Academy. This is our NIMSET series in which we are currently dealing with the chapter Quadratic Equations. And till now, we have already done 6 parts, and you might have got a good grasp on the concepts and some expertise in solving the problems as well. So now in this part 7, this is again a practice session in which we'll be going through a number of problems in order to get a deeper understanding of how things work. After this, you will be in a definitely a better position for conquering the problems that you encounter in the exam. So let's get started. Starting with the first problem of the day, we have been given two quadratic equations, Q1 and Q2, and they're saying that Q1 and Q2 they have both the roots as common, not just one root common, but both of the roots are common in them. Then in that situation, K is A times of Q, where A is an integer. We need to find out what is the value of A. So that is the problem. We have already seen the concept of common roots earlier, but there were two cases involved. One was both roots as common, and another was one root as common. So for this, we have already devised a formula that in which condition does this hold true. And for both roots as common, we had mentioned a statement that this is only possible. Let us say you have been given the two roots as alpha and beta. Then using these two roots, you can form just one quadratic equation, and that would be x squared minus alpha plus beta x plus alpha beta equal to 0 using the sum and the product rule. But now here the thing is, this is our quadratic, let us call it Q. And now what we can do is we can multiply this entire quadratic Q with some constant K, so that it now becomes K times Q, which means Kx squared minus K times alpha plus beta x plus K times alpha beta equal to 0. Now you will ask if it is the same quadratic or a different quadratic. If we take out the K as common and cancel it out, then it will definitely get converted back into the same quadratic. But then what is the difference between the two? Are they same or different? So for this, conclusively, we can say that these can be said to be two equivalent quadratics, not actually equal quadratics. Let us call them as Q and Q dash, such that one relation that holds true between them is Q dash will be some constant times Q. That is what we saw over here. For this quadratic as well, the roots are still same. If you take the sum of the roots, it is still K times of alpha plus beta upon K, which is nothing but alpha plus beta. Similarly, the product is K times alpha beta upon K. So both these Q and these Q dash will have the same roots, and still they are not the same quadratic but equivalent quadratics. So when does this hold true? When both the quadratics are multiplicative of each other, which means you can multiply a given quadratic by some constant and get the other one. More precisely, we can put it in this particular way for better understanding, so that there remains no confusion about this. And that is why we have taken this question today, so that this concept does not get skipped out. So let us say there is this Q1 as a1x squared plus b1x plus c1 equal to 0, and we have a Q2 as a2x squared plus b2x plus c2 equal to 0. Now if I say that Q1 and Q2 have both the roots as same, then you will not directly say that Q1 is equal to Q2, because it is possible that Q2 is some constant times Q1. They actually are equivalent of each other. There would be some constant multiplied throughout the given equation. So in such cases, how we deal is, instead of directly comparing the coefficients, we will do it something like this: a1 by a2 equal to b1 by b2 equal to c1 by c2 equal to some constant k, by which q1 was multiplied, and then as a result we got q2. So this is the condition that we use when it is stated that both the roots are common, because in that case all the coefficients would be multiplied by some constant k. So this is what we are going to use in this particular question as well. So now let us see how that can be done. In the same condition, we will note down all the coefficients and then we'll proceed accordingly. So here the coefficients a1 and a2 are 6p plus 2 upon 12p plus 4. We'll equate them with b1 and b2. b1 is q, b2 is k, and c1 c2 gives 3p minus 1 upon 6p minus 2. So now from here we can clearly see that the first term, that is a1 by a2, converts into 1 by 2. Similarly c1 by c2 also converts into 1 by 2. So that simply means that q by k, which is b1 by b2, will also be 1 by 2. So that implies that k equal to 2 times of q. And here they were asking us the same thing, the value of a, which in this case becomes 2. So that would be our answer. But now you might ask, what if these a1 by a2 and c1 by a2 would have given us different values? In this case, both of them reduced to half, right? But if they would have been different, then the question would have been incorrect. It was not possible in that case for q1 and q2 to have both the roots as equal. So this is how such problems can be approached. Now let's move on to the next problem. Further, let us revise both of these concepts that we just saw at a glance. In the both roots scenario, we just saw that the condition that we need to use would be a1 by a2 equal to b1 by b2 equal to c1 by c2, that is some constant. So now taking these one at a time along with k, we can easily devise whatever has been asked. The possible questions in this are, you will be given one quadratic and some coefficients would be hidden in the other quadratic and they will ask you the value for those. So it can be easily done with some simple ratio and proportion manipulation. So we cannot expect a difficult question coming from this particular type. And then coming to one root common, for this we have already seen a formula that was a1c2 minus a2c1 the whole squared equal to a1b2 minus a2b1 multiplied with b1 c2 minus b2 c1. And in order to remember this also, we have seen a method in which we used to write all of them like this and then we used to do this cross multiplication kind of thing by which we can derive this formula. But as you might be remembering that during the derivation at one step we had encountered something like we substituted alpha as the common root in both of the quadratics q1 and q2 and we had got something like this, alpha squared equal to b1 c2 minus b2 c1 upon a1 b2 minus a2 b1. Similarly, we had got alpha equal to a2 c1 minus a1 c2 upon a1 b2 minus a2 b1. And now using these only we had eliminated alpha and then we had reached to this particular condition. But when you are asked for the common root itself, then there is no need to go up to this formula because this simply states whether the roots will exist, common root will exist or not. It is a relation between all the coefficients itself, but it does not involve the common root. So for that we can stop here itself and we can directly find the common root using all the coefficients when they are available to us. So using these only we can derive another formula which you might have already seen because this concept must have been introduced to you in your school time itself and there you might have been using this particular formula which is applicable in some cases as well. And using that only we can derive our original condition that we saw very easily. So that formula is something like this. we will write alpha squared upon b1 c2 minus b2 c1 equal to minus alpha upon a1 c2 minus a2 c1 equal to 1 upon a1 b2 minus a2 b1. So you can also remember this one instead of the original condition which we have seen. And talking about the derivation part, it again gets derived from that simple thing which we have seen. We will write all the coefficients spread across like this. Then for this alpha squared term, what you will be doing is you will ignore this first column and you will look at these remaining two columns. And from them, you will take the cross multiplication b1 c2 minus b2 c1 from downwards to upwards. So that's how we get this particular term. And then moving to the second term, here we have got minus alpha. Why do we get a minus over here? We'll just see. Similarly, for that derivation, now what we are going to do is we will keep this second column intact and we'll use the other two, a1 c2 minus a2 c1. But as you can see, the relation is different over here. We have to come from top to down and then down to top, a1 c2 minus a2 c1. So that is how it is. Here when we do that, the sign gets changed because even you have seen that in the sum of the roots also there is a minus sign involved. So that is what brings that over here as well. So either you can remember this to be minus alpha over here, or you can change this equality at the bottom into a2 c1 minus a1 c2. If you have to keep it in the same top to down fashion, then keep a minus at the top. Otherwise, change it to this way. So either way, however you like to remember. And then coming to the last one, here we will keep the third column intact and use the other two as a1 b2 minus a2 b1. So that is how we get this particular equation equality, using which you can directly substitute. If you have all the coefficients available, then you will get all the denominators. Then you can play around with the values of alpha squared and alpha and get the exact value of the common root. So this is also how such questions can be approached. And if you have to deal with the just with the coefficients and not with the common root itself, then you can go for the formula which we have earlier derived. So that is how such problems can be done. Now let us have a look at the next one. So now we'll be looking at the application of the new formula which we have just seen. There are these two quadratics given to us and they have one root as common, and we need to find the value of the coefficient a, which you can see it is at both of these places. So b1 and c2, both of them are a itself. So now you can go with both of them either with formula 1 or formula 2. They are both same actually. They are just derived at the different steps of derivation. We get the second formula earlier and then using that we reach to the earlier one. So you can go with either of them. So now let us, as we have learned the second one, let us go with it. We will call the common root to be alpha. And then we can say that alpha squared upon b1 c2 minus b2 c1 equal to minus alpha upon a1 c2 minus a2 c1 equal to 1 upon a1 b2 minus a2 b1. So here let us note down what are a1 b1 and c1. That would be easier. So we get a1 as 1, b1 as a, and c1 as minus 1. a2 as 1, b2 as 1, and c2 as a again. So now we can simply substitute the values over here and we get alpha squared upon b1 c2, which would be a squared, minus b2 C1, that would be minus 1, so this becomes plus 1 equal to minus alpha upon A1 C2, that would give A, plus 1 equal to 1 upon A1 B2 minus A2 give B1 gives us 1 minus A. So now here simply what we get is alpha squared equal to A squared plus 1 upon 1 minus A, and minus alpha equal to A plus 1 upon 1 minus A. From this we'll get alpha equal to A plus 1 upon A minus 1. So now the next thing that we are going to do is simply we will be eliminating alpha from here, and we'll just use these two. So now it must have a strike in your mind that there was actually no use of taking the second equation, because we are not dealing with common root itself. We are not concerned with value of alpha. What we are concerned with is these unknown coefficient A. So here we could very well use the second one that involves the relation just between all the six coefficients. So that formula would have been easier over here. But still we can proceed with this as well. No issues with it, because both are actually the same thing itself. There is not much difference, just that one is more mature than the other. So now here we'll say alpha a square plus 1 upon 1 minus a, which is the value of alpha squared, that would be a plus 1 upon a minus 1 the whole square after eliminating alpha. So now we'll say that a square plus 1 upon 1 minus a equal to a plus 1 the whole square, and to this we can write as a minus 1 the whole square as well without any issues. So that one time it gets cancelled out. Then we'll get a square plus 1 1 minus a equal to a plus 1 the whole squared. So now we can simplify this and find out the value of a from there. So let us check out what are we actually getting. After expanding this, we get a squared minus a cube plus 1 minus a equal to a squared plus 2a plus 1. So now a squared is cancelled out, 1 is cancelled out. What we are getting is minus a cube equal to 3a. So this can be written as 3a plus a cube equal to 0. Here we can take 1a as common and write that as a squared plus 3 equal to 0. So from here we get one solution as a equal to 0, and another solution would be a squared equal to minus 3, which means a equal to root of minus 3, which is nothing but iota root 3, and obviously with a plus or minus sign. So this will have three roots. A can be 0 or a can be plus or minus of root 3 iota. So we have got three values for this coefficient a, and then depending upon the option you will be choosing which one of them is true. As of now we will have to go with all three. There is no way that we can eliminate one or more of them. So this is how this particular problem will be solved. Now this one is an easier problem. It would have directly strike to you that what we'll be using in this. A quadratic has been given and they are saying that one root is 3 minus iota root 5. Then find out the values of m and n. So now here looking at one root, that is 3 minus iota root 5. What comes to your mind? Can you comment anything about the nature of another root? Yes, we can do so, because this root 1, it is not a rational root, it is irrational. It is in the form of a surd. This is what we call a surd. So yeah, you have already seen this maybe in your class 9 or so, and you have already learned that the roots always exist in pairs. So if one root is this 3 minus iota root 5, then another root has to be a conjugate of it. This happens in case of irrational roots. We get both the roots in pairs and they are conjugates of each other. Which means if one root is this, then another root has to be 3 plus iota root 5. Which means both the roots are known for the given quadratic. And when both the roots are known, now what lefts? You can simply use the sum and the product thing to get the results. We will get sum as 6 and product as 3 minus iota root 5, 3 plus iota root 5. That simply becomes 9 minus iota root 5 the whole square, that is iota squared is minus 1. So when you will take the iota square and this minus, it will get converted into 9 plus, and root 5 squared is 5, so that is 14. So we have sum as 6 and product as 14. So now let's get back there. Our sum is m, so that will become 6, and our product is n, so that will become 14. So we have easily devised the values of m and n using this simple property that irrational roots will exist as a conjugate pair. In case of rational roots, it is possible that one is 6, another is 14 or anything, just the numbers which we saw over here. That is possible. You can have 6 and minus 6 as well. There is nothing rule, nothing kind of a rule over there that they should exist one positive, one negative, or nothing about the nature of the roots can be stated for sure there. In case of irrational roots, they definitely have to be in the form of a conjugate pair. So this is what you can remember, and using the simple trick we could very easily solve this particular problem. Next, coming to this one, we have been given two quadratics q1 and q2, and there are these four options. They are saying that both q1 and q2 have real roots, at least one of them have real roots, both have imaginary roots, at least one have imaginary roots. So now if we have just one single quadratic equation, then we know that if d is greater than 0, then we will be having real roots. If d is less than 0, we'll be having imaginary roots. Even for d equal to 0, we have real roots, but they are equal. So these are the two cases in case of a single quadratic. Here we have q1 and q2. Let us say for q1 we will get the determinant as d1, for q2 we'll get the determinant as d2, but we cannot directly comment upon the nature of both of them together. Let us see why. First we'll try to find out what are the values of d1 and d2. So here what will d1 become? It will be b squared minus 4ac, which is 4p squared minus 4q minus 1. Similarly, d2 will become b squared, that is q squared minus 4ac. Here it is 16p minus 1. So now here p and q are common in both of the equations, and we do not know what is the relation between them. So just looking at this particular thing d1 or at d2, we cannot comment about their nature, whether they are positive, negative, or 0. We don't know anything. So now here what the question is expecting us to do is we'll have to use both d1 and d2 together. Then maybe we are in a better position to claim whether that thing is positive, negative, or 0. Let us simply try adding the two if we can get something in a better format. This will become 4p squared minus 4q plus 4 plus q squared minus 16p plus 16. So that becomes 4p squared plus q squared minus 16p or we can write it p terms together and then q terms together as 4p squared minus 16p plus 16, then q squared minus 4q plus 4. Now, can we simplify these even more? Yes, it seems that it'll be possible. Let us write that over here only because of lack of space. Okay, so from these p terms, we can take 4 as common, then that will become p squared minus 4p plus 4, q squared minus 4q plus 4 as it is. And now we can write this as 4 times p minus 2 the whole squared plus q minus 2 the whole squared. So that is what we have got the sum of d1 and d2 as. And now we can simply write that as something 4 capital P squared plus 4 capital Q squared. So now looking at this, can you comment about its nature? This is a whole square, so it will definitely be positive. This is also a whole square, so it will be positive. So their sum will also be positive, which means from this you can comment that d1 plus d2 is greater than 0. You do not know if they are individually positive, negative, 0, whatever. But we know for sure that their sum is definitely positive. So from this, can we say anything conclusively about their nature? Let us think for a while and then we'll try to analyze this fact. Let us erase this down. Alright, now when we know that the sum of any two numbers is greater than 0, which in this case is d1 and d2. When sum of any two numbers is greater than 0, then for sure at least one of them has to be positive, right? Both of them cannot be negative. If I have minus 4 and minus 2, can their sum be ever positive? No, it cannot. If I have one negative and one positive, so in this case it's not possible, but if this positive number were greater in magnitude, then the sum would have been positive. Similarly, if both are positive, then definitely the sum will be positive. And if one is 0, then also the other has to be greater than 0, then the sum would be positive. So looking at these four cases, what can we say about the nature of d1 and d2? We can say that if their sum is positive, then at least one of them should have been greater than 0, right? Are you convinced with this? If the sum of two numbers is greater than 0, then at least one of them has to be positive. And when exactly one of them is positive, then it has to be greater in magnitude than the negative one. So that is understood, right? So here the only thing we need to get convinced of is that when sum of d1 and d2 is positive, then at least one of them would definitely be positive. And now, using this particular fact, what can we say about the quadratic equations? If at least one of d1 and d2 is positive, which means at least one of q1 and q2 will have real roots. That is a direct implication. And that's what was the essence of this particular question that we need to catch and understand. And that is what analysis we have done. We could not individually would have been able to comment about the nature of d1 and d2. So we simply combined them. We took their sum that turned out to be positive. And now using this particular fact, we are claiming that if the sum is positive, then individually we cannot comment, but at least one of them will definitely be positive. And hence, at least one of q1 and q2 will have real roots. So that is what brings us to this option B. Definitely both of them can also have real roots when it is this particular case. or this fourth case. In this case, one will have equal roots, but that also gets counted in real itself, right? So at least one will definitely be having real roots. Both are also possible. We will go with this option B for this. Now we'll be exploring the different cases that arise out of it. The question which we have just seen, there were two quadratics Q1, Q2 having their determinants as D1 and D2, and we could not individually comment about their nature of the roots, so we just combined the two together. In that case, we have done addition, but it is also possible that we go with the product. And let us see what are the different cases that arise out of it. This was the case that existed there. D1 plus D2 was positive. So if sum of two numbers is greater than 0, then at least one of them has to be positive. So that implies the fact that at least one of the quadratics will have real roots. That is what we did in that question. Then next, if their sum turns out to be negative, then what can we say? If the sum of two numbers is negative, then at least one of the numbers will be negative. Using the same discussion which we saw in this case 1. Using the same arguments, we can say that if sum of two numbers is negative, then at least one of them will be negative. Both negative is also possible, at least one will be negative. And hence, at least one of the quadratics will have imaginary roots. That is what we conclude out of it. Now coming to the product, if the product of D1 and D2 is positive. So now here we again get two cases, either both are positive, so their product will be positive, or either both are negative, then also their product will be positive. So these are the two cases. So if it is this particular case, then both roots are real. But if it is this particular case, then both the quadratics will have imaginary roots. So here, either both the roots can be real or both the roots can be imaginary. That is what we can conclude from this. And even the greater than or equal to 0 case can also be accommodated within that. Then coming to the last one, when the product is negative. So here definitely one of them will be positive and one of them will be negative. So one root is positive and one root is negative. So we can say for sure that one of the two quadratics will be having real roots and one of them will be having imaginary roots. So this is what these four cases tell us, and this is very useful in the situations where we cannot individually comment upon them, but together using their combinations we can comment about the nature of roots of two quadratic equations at once. So this is also a technique from which you can expect some questions, and that is not that difficult to solve. As we have seen, we just need to combine them and check for their sign, if they are positive, negative or 0. So now moving on to the next one. So here we are having a quadratic given to us in which the coefficients are a and b such that they lie in this particular domain, and we have been asked find the number of possible quadratic equations having real roots, which means we can substitute different values of a and b from this particular set, and as a result different quadratics will arise. What is the total number that we can get? For A we have 5 choices, for B also we have 5 choices, so in total there are 25 possible equations that we can get, but not all of them will be having real roots. So we want only those which will be having real roots. So how we can proceed for this is, first of all we'll go for the condition of real roots, that is D greater than or equal to 0, which means B squared minus 4, that is 4 times 7 28, A has to be greater than or equal to 0. So that is B squared has to be greater than or equal to 28A. So this has to hold true for whatever values of A and B we pick up from this particular set. So now we'll be picking up values one by one. and we'll be checking if this condition is satisfied or not. So here let us take values of b, and here we'll be taking the corresponding values of a. For b, if we take 1, then is there any value for a in this particular set such that this will hold true? If there is 1 on this side, then it can never get greater than or equal to 28 times something when a is an integer taken from this set. So there is no possible value of a in this case. Similarly, when we take 3, 3 squared, 9. 9 will never be greater than or equal to 28 times something. So no value over here as well. When we take 5, this side gets 25. Again, no value for a. Then when we take this as 7, b as 7, then left side becomes 49. Now this 49 will be greater than or equal to 28 times 1. When we take a equal to 1, it will hold true. When we take a equal to 3, then it becomes 28 times 3, that is 8 3 is 24, 84. So it's not holding true. So there is only one possible value for b equal to 7, that is a equal to 1. Finally, when we take b as 9, then this side becomes 81. So for a, we can take 1 and 3 in this case. So as a result, we have got only 3 possible pairs of a and b, which is 1, 7, or you can write it this way, 1, 9 and 3, 9. So with these 3 pairs, we can form only 3 quadratic equations such that it will be having real roots with values of a and b taken from this particular set. Using these values, you can also write the actual equations that we are getting out of this. So again, this was an easy question which you can expect in your exam. Now coming to last problem for the day, we are having this particular quadratic given to us, and it has been said that it has 2 distinct real roots, which are x1 and x2, such that the difference of the roots is less than 1. So they are asking us that this particular coefficient a lies in what range. That has to be found out. So here we are having 2 different conditions. First one is that the roots are distinct real, and second condition is about the difference of roots. So using these 2 conditions, we'll try to estimate what is the range of values that a can take. So using the first condition, we can write that the d determinant for this quadratic has to be greater than 0. The equality will not hold over here because the roots are strictly distinct. So from this, what we get is d greater than 0, which means b squared minus 4ac, 9 minus 4a squared greater than 0. So from here we can simplify it as 3 minus 2a, 3 plus 2a is greater than 0. We can draw a number line, minus 2 by 3. Here this will be having 2 solutions. This is actually minus, yeah, it is minus of 3 by 2, and this is plus 3 by 2. Now we want their product to be positive. So which values we'll be taking? We already are aware of this method, that we draw a number line and then we estimate. Let us say for this particular side, we will take some greater value for a, let us say 10. When we take 10, then this will become negative, this will become positive, which means the result is negative, positive, negative. And since we want the positive part, so from this first condition we get that a lies in the range of minus 3 by 2 to 3 by 2. That is what we get from the first condition. We'll also find out from the second condition, and then we will take the intersection of the two. So now for the second condition, that is about difference of the roots. We already know the formula for the difference of the roots that we have seen to be root of d by modulo a. This is what is the difference of the roots. So in this case, that will become root over of 9 minus 4a squared upon modulo a. This difference has to be less than 1. So I will be solving this inequality. Because this modulo is positive, so we can shift that to the other side. The equality will not change. So we get this less than mod a. We can square on both sides without any issues. 9 minus 4a squared is less than a squared. So 9 minus 5a squared is less than 0. This is what we are getting from here. So 3 minus root 5a, 3 plus root 5a has to be less than 0. So again we will be drawing the number line, and here the points that we'll be plotting will be minus 3 by root 5 and plus 3 by root 5. Again, in order to estimate the sign, we can substitute some larger value of a, let us say 100. In that case, this will be negative, this will be positive. So we are indeed getting a negative over here. That is what we want. So it will be negative, positive, and negative. So now let us clear this out. And from the second condition, what is the range of values of a that we are getting, that we need to find out. So here there are two portions of the line that we are interested in, and that gives us the range of a as minus infinity till minus 3 by root 5 union 3 by root 5 till positive infinity. So these are the two range of values of a that we have got, but now we will be required to take the intersection of these two. So for that we will need to compare the values, which one is greater among 3 by 2 and 3 by root 5. We know that 3 by 2 is 1.5, and talking about 3 by root 5. Root 5 is approximately 2.23. So this is 3 by 2.23, which will be approximately, you can directly compare the two, that this will be less than 1.5, which means this particular value is greater. So if we want to take the intersection of the two, it will be easier if we go with the number line again. You know that 3 by 2 is greater, so it will lie over here. Then here we will be having minus 3 by root 5, 0, 3 by root 5, and 3 by 2. And now let us see which are the feasible regions that we have. We wanted value between minus 3 by 2 and plus 3 by 2. So it says that this particular region is feasible. And the second inequality says values less than minus 3 by root 5 till infinity and values greater than 3 by root 5 till infinity. So these are the portions that we got, and taking the intersection we get these two regions as common, which means the solution set for A will be minus 3 by 2 till minus 3 by root 5 union of 3 by root 5 till plus 3 by 2. So this is the range of values that A can take, such that the given quadratic will have two distinct real roots, as well as the difference between the roots will be less than 1. So this was one of the lengthy problems that we saw from this particular chapter, and that's all for today. In the next part, we'll again have a look at some more problems. It will also be a practice session. And then at the end of it, you will be getting some problems to practice on your own. We'll be dealing with some PYQs and the most expected questions from the exam point of view. And that is how we will be concluding this particular chapter. So till then, you can post and comment whatever queries you are having regarding this particular chapter or anything else about the exam. And stay tuned with ACC Academy.